Hello student, very good morning to all of you. I hope you all are happy, healthy and fine at home. What did we discuss yesterday, or what were we discussing yesterday? I think, do you remember what were we discussing yesterday? I think we discussed about some general term used in the retrosynthetic analysis or in a strategy while using the Chiron approach or Chiron perspective. So what are the terminologies, and in this point we are going to learn the 6 target molecule. Number 1 is S-propane diol, second one is L-alanine, then third one is epiclo plus minus RS epichlorohydrin, then multistatin, pentinomycin and cyclamic acid. These are the 6 molecules we are going to discuss one by one and with their detailed retrosynthetic analysis as well as synthesis and somewhat mechanism whenever it is possible or necessary. In that way we are going to study. So let us begin with the first one, that is a S-propane diol, right? S-propane diol, it is a target molecule, and target molecule we know that the molecule whose synthesis being planned is known as a target molecule. Here clearly you can see propane. You know there are the 3 carbon atoms are there. No double bond or single bond, so no double bond or triple bond, simple propane you have to draw, and the diol there will be 2 hydroxy groups are there, and that's why the structure of propane diol you might be knowing here. This is a structure of propane diol, here OH and OH. This is the structure of propane diol, CS3OH, OH here. And the first thing what we are going to learn, first one, this is our target molecule, right? And then first point here we are going to learn first one, A point, or what we can call it, first one is a RSA. RSA is nothing but as a retrosynthetic analysis. Retrosynthesis analysis we are going to learn here. Retrosynthetic analysis. And as we know that, what does it mean? Retrosynthetic analysis means what? The process of breaking down the target molecule into convenient starting material is known as retrosynthetic analysis, right? And now here the structure of S-propane diol, we know that this one CS3, then OH and here OH. I am writing the functional group which you can see clearly. Another thing you are knowing that at this corner point there will be a carbon atom, at this corner point that carbon atom bearing 2 hydrogen atom. Here also 1 hydrogen atom is missing. As you know that there is carbon atom, methyl group shown at the end. So this is the structure of S-propane diol. This is the structure of S-propane diol. Why S-propane diol? Propane diol. This is the structure of S-propane diol. Now what will this we know that this is one of the arrow. This arrow generally used in the retro. There are the various arrows are applied or using in the organic chemistry. Suppose as this is called as a simple arrow. So this simple arrow indicate react to give whatever substrate or the reactant or the starting material. Whenever we are adding reagent, that react and to give the product or whatever intermediate transition state or that type of the things. So this is the meaning of this arrow, react to give. And one arrow we are showing like this. So right, this is the one of the arrow, this type of the arrow, double headed arrow. This double headed arrow we are using in the while drawing the resonating structure, right? They are showing interconvertible of structures are there. So these in case of the benzenes are there, we can put the alternative carbon-carbon double bond in one and another one, and so that type of the arrow indicate as a canonical form or resonating arrow or interconvert. And now sometime we are showing this type of the arrow, and this arrow specifically used in the retrosynthesis. It could be made from, this is called as a could be made from means this could be made from this compound. So that is the meaning of this arrow, and sometime it is shown as a this type of the arrow, right? This is at an equilibrium arrow. These two structures are interconvertible to each other. Sometimes it is written as a, this is also as a disconnection arrow in the while showing as a reaction mechanism. We generally showing the breaking of arrow or arrow pushing concept. At that time you might have learned or you are knowing this type of the arrows are there. Or sometime it is written as a this kind of the arrow like this. This is a only one side. This is called as a fish hook arrow. In generally homolytic fission or photochemistry, we are using this type of the arrow. These are the certain arrows and their meaning, we know that. And now this is a disconnection, and as we know that disconnection means what? An analytical operation which break a bond and convert a molecule into possible starting material is known as disconnection, right? So this is a disconnection, and there we are using a one term is a FZI. FZI is written over this arrow, means one of the functional group is converted into another functional group, so that disconnection becomes possible. So that we can write here on the arrow we can write FZI, functional group interconversion. So this functional group, this methyl group, we can convert, these hydrocarbon can be converted into as a most reactive functional group, maybe as a CHO, and rest of the thing we are putting as it is, OH as it is, this one also as it is, OH, right? OH. What we did here, we show this functional group means what? Functional group interconversion. One of the functional group is converted into another functional group, so that disconnection becomes as a possible. That is our aim over here. Now another one, or we can show, or means this or that one. Here you can get this compound from this also OH, here OH, and here also OH. That is a glycerol. We know that this is a glyceraldehyde. Everybody know that glyceraldehyde, it is one of the starting material, or we can call it as a precursor for the synthesis of the carbohydrates. At that time we will see in detail, but this is one of the, and the name of this compound is a glyceraldehyde, or generally we are referring as a D-glyceraldehyde. Why D-glyceraldehyde? Because look at here, from the bottom you have to consider this part only while assigning the relative configuration. This lower side you have to second carbon atom, there the hydroxy group is here in this case, particularly in the glyceraldehyde, the hydroxy group are on the right hand side, and therefore it is designated as D, or the letter D is written over here, and the name of this compound is D glyceraldehyde. And this, there are 3 OH, adjacent OH are there, and this compound is known as a glycerol. This is known as a glycerol. OL indicate as a hydroxy groups are there. If number of hydroxy group goes on increasing, the viscosity also goes on increasing. That is another one physical property of that molecule, and the rate of flow of that is decreases, I think. That is the physical property, but here just remember as this one. And now again this can be converted into FgI functional group conversion, functional group interconversion. One of the functional group is converted into another functional group, so that this connection becomes possible. Or what do you get here? You can convert this molecule with, you will get here OH. I am writing here only as a specifically hydroxy group. Here C OH, 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 here HO, here HO. This is known as D Manitol. D, why D Manitol? Just remember here, this you have to consider here the hydroxy group again on the right hand side, and therefore this is called as a D Manitol. D Manitol. Mannitol. This is the structure of D Manitol, and D Manitol can be obtained from D Mannose, and that is a sugar which is readily available in the nature, right? D Manitol can be obtained from D Mannose. The structure of D Mannose will be this one. Here is a open chain compound CHO, then there are HO, HO, and here we can write OH, OH, and another OH. This is called as a D Mannose. D Mannose. And OSC, OSC, OZ is called as a sugar unit, and this is a readily available. If you write in this way, you will get as a 2 mark. Suppose 4 mark question is there, 3 mark question, 1/2 mark you will get for the retrosynthetic analysis. Understood this? What does it mean? Retrosynthetic analysis means what? Retrosynthetic analysis means what? The process of breaking down the target molecule into convenient starting material is known as a retrosynthetic analysis. The process of breaking down the target molecule into convenient starting material by using disconnection and FGI is known as retrosynthetic analysis. I am repeating this word again and again so that you can understood this concept very clearly and nicely. Look at, this is a retrosynthetic analysis of this first molecule, which is a S-propane diol. Why it is S-propane diol, I already told you in my previous lecture, yesterday's lecture. This OH, so this is only how many chiral carbon atoms are present in this case? There are only one chiral center is present. This is a chiral center, and chiral center is always denoted by the asterisk or that star. Here only one chiral center. Here how many chiral center? There OH, OH, that become as a symmetrical one. So there 1, 2, 3, 4 chiral centers are there. Here 1, 2, 3, 4 chiral centers are again present in the D Mannose. Chiral center means 4 different group attached to carbon atom. That center is known as a chiral center or asymmetric carbon atom. So this is a retrosynthetic analysis. Understood this one? Now this is a reverse reaction. Retrosynthesis means what? An imaginary but logical reverse chemical an imaginary but logical reverse chemical reaction which help us to reach the reactant starting from the target molecule, and this is our target molecule. You can call this one is a chiral, and this you are getting as a chiral precursor or the template. And whatever symmetry or a carbon framework or what we can call it as whatever are there in the precursor, that must be present here. That segment should be present, apparent in the target molecule, and that's why that type of the thing we are using. This is a Chiron approach or the Chiron perspective. Here they look at this type of the symmetry may be preserved there, and that's why this is called as a chiral precursor. Chiral precursors which is available, the cost of that cost also as a then stereochemistry, stereochemical control, then chiral sense of chirality means that type of, and the carbon framework, and in a carbohydrate type of the symmetry, these everything is included there, and that's why from starting with this we can synthesize this molecule here by using the suitable or the proper reagent and the keeping the suitable reaction condition. We will prepare this compound. Now let us look at as a synthesis of this. Synthesis. Now we are going to start from this side, right? D Mannose is a starting material or which is a precursor over here. Now this is a half mark you will get there, means one, suppose 4 mark question depending upon the nature of the question, how much weightage is there. Suppose sometime is a 4 marks, sometime maybe as a 6 marks, sometime maybe as a 3 mark. So suppose depending upon that you will get as a mark. Half mark means 3 marks, so 1 half mark you will get for the retrosynthetic analysis. Now is a synthesis, actual synthesis here. Second part will be the synthesis here, right? Synthesis, actual synthesis. In the laboratory, how you can actually synthesize in the laboratory, that we are going to learn over here. Now from this, now is a forward reaction. From this you can prepare this, from this you can prepare this, and from this you can prepare. So that is the meaning of that synthesis. We are going to recollect this by using proper or the suitable reagent and keeping the proper reaction condition. So let us start the synthesis. I think let me clean the board first and we will see the synthesis of this molecule, right? Now let us see here the beginning. We have let us take the starting material. This retrosynthesis we have over here. Now is the second part we are starting, the which is the synthesis. Second one is a synthesis. Now is a synthesis, right? In the synthesis, starting compound just now we have seen, keep in mind that. What is that? D Mannose. We know that the structure of D Mannose, this one at the top is aldehyde group is there. On left hand side there will be a 2 hydroxy group, right? And on a right hand side there will be a 3 hydroxy group, OH, OH and OH. Molecular formula you know that, C6H12 and the O6, that is the molecular formula. And this is a D Mannose and D glucose. Do you know that the relationship between these two, D Mannose and D glucose, they are epimers of each other. This type of the epimer anomeric effect or the anomeric center in detail we will learn when we are going to study the carbohydrate chemistry in the section second. So this is the structure of D Mannose, right? This is the structure of D Mannose. And OSE, last suffix or last 3 word OSE indicate as a sugar. OSE in a Greek word I think it is. And now when this one is treated with the reagent, proper reagent you have to use over there. So what you are going to do, this aldehyde you are going to convert into as a alcohol, primary alcohol. what will be the reagent? Can you think? Do you remember? The aldehyde group, there are a number of reducing reagents are there. For conversion of aldehyde group into as a alcohol, one may be as a sodium in presence of ethanol, or what we can call it as a sodium borohydride, lithium borohydride, Wilkinson catalyst. These are the number of reducing reagents which can reduce the aldehyde group into as. But the proper here in this particular synthesis, what the scientists they have selected the proper or the suitable reagent for this is a sodium hydroxide. Sodium borohydride NaBH4 is known as a sodium borohydride used in presence of the methanol. MEOH, methanol. Me stand for as a methyl group. Methanol, what it will do? It will convert aldehyde group into as a primary alcohol, so that you are going to get the structure over here. This one I am writing OH, 2 hydroxy group, they are on the left hand side, and now 3 hydroxy group, they are on the right hand side. Now tell me, there are number of hydroxy groups are present over there, right? This is a structure of D Manitol, right? Structure of D Manitol. This is a structure of D Manitol. Now in a D Manitol, how number of hydroxy groups are there, and these hydroxy group, we know that they are categorized into 3 classes: primary alcohol, secondary alcohol, tertiary alcohol. Likewise they are classified, but here how many type of the alcohol you are going to see? Here primary alcohol, 2 primary alcohols are there. Terminal are the primary alcohol because this hydroxy group connected to CH2 group, and here but these are 4 are the secondary alcohol. Now here suitable reagent is used here. This is a structure O in presence of H plus CS3, and normally this one CS3 C double bond O CS3 is known as a acetone. This is known as a acetone, right? And H plus, while protection and deprotection we already use this reagent. This reagent is used to protect 1,2-diol. 1,2-diol means vicinal diol get selectively protected, and you can carry out the reaction to obtain the desired product, and that is the main purpose, main aim, to protect the 1,2-diol. How many 1,2-diol? They selectively protect the terminal diol here, 1 and 2 here also there, and these 2 secondary that remains there, they are trans to each other. This CH2 we can rotate easily, though even I am writing like this, but it may be as this way, and therefore this acetone can be easily get protected. How I can show this one? Let us look at this one very easily. If you pay the attention from the beginning, it will be very easy to remember this one. Now this O, and I am only this one, it means that this is a methyl group, this is also as a methyl group. Sometimes it is referred as a Me, but in a carbohydrate chemistry that type of the things are written, so I don't want to confuse you, but remember this terminal is nothing but as a methyl group, this is also as a methyl group. Now one of the secondary alcohol on a left hand side, another this OH should be, it remains on the right hand side, and this again get protected, so I am showing like this. This is again is a very easy to draw only this line to show the clarity of this molecule, and so this is a protected D Manitol, and now this is treated with some suitable reagent like PbOAc4. This PbOAc4, the name of this reagent is known as tetraacetyl lead. This is called as a lead or lead tetraacetate. You can call it as a lead tetraacetate. Tetra means these 4, and OAC acetate, tetraacetate. That is a lead tetraacetate. How we can show this lead tetraacetate? Means this is a PB means lead. Here OAC. AC means you might be knowing, you are familiar this word already. AC means acetyl group, like this. Acetyl group are written like this. C double bond O CS3. This is acetyl, and O is there, means this group. This is called as a OAC, right? So this you should remember. The purpose, the aim of this reagent used particularly in the carbohydrate chemistry, it is broken as a symmetrically from here like this. We will see the mechanism how it will break, and we are going to get here the group. And after breaking this bond, what do you get? Aldehyde. 2 moles of this compound. One is a CHO, and I am writing here O and this group, right? So exactly cutting from the middle, you are going to get this type of the protected glyceraldehyde, and this protected glyceraldehyde further treated with, I am showing as a this arrow, this 2 is nothing but as a 2 moles of this. You are getting 2 moles of this protected glyceraldehyde, and after that you want to reduce that carbonyl group by using as a suitable. I am repeating the word here. Use the proper reagent so that it can be converted into the suitable reagent. So here use as a Rane nickel. You might be knowing Rane nickel. What it will do? It will the reducing reagent. Again it will reduce the carbonyl group into as a primary alcohol, and you are going to get the structure is this one. There OH and this one, right? This protected group still remains as it is. The Rane nickel only converted that group, aldehyde group, into as a primary alcohol, right? And now this further treated with another reagent is called as a TSCl in presence of pyridine. Pyridine used as a solvent here, which will protect the proton adjacent to that oxygen atom, and tosyl group get attached over there, and that hydroxy group, as we know that it is a bad living group, and we are converting by using this tosylate group the good living group. So what do you get over here? You are going to get the compound over here like this, the OTS, that is a tosyl group, and this remains protected over there, right? And after this tosyl group is a good living group. You might be know the structure of this. This is the structure of this CS3, then I think yes, double bond O Cl. This is called as a tosyl chloride, TSCl. This part is a TS, means tosyl chloride. This is known as a tosyl chloride, and that tosyl chloride, after this tosyl chloride is a good living group or the excellent living group. Why it is an excellent living group? And then this compound further treated with sodium iodide in presence of the acetone. Here in this case, sodium iodide NaI in presence of acetone. Here the acetone only used as a solvent for dissolving purpose of this sodium iodide. What it will do? That sodium iodide is a good living group. That is a good nucleophile. It can attack to that CH2, and we are going to get this one is a living group, and therefore while looking as a mechanism, while studying the mechanism we will see detail, but that iodine can attack over here and this get departure of that living group, and you are going to get over here the I and this one O and this type of the protecting group, right? This iodine and further treated with, this will be further treated with that is a dehalogenation, again treated with the Rane nickel. Here the Rane nickel use again here Rane nickel. What it will do? It will remove or zinc dust in presence of the acetic acid can be used for conversion of this. First Rane nickel, what it will do? It will convert this, remove this group, and you are going to get as this type of the compound, right? And this further treated with aqueous H2SO4, that is what we can call it for the deprotection in presence of this aqueous in acidic medium. This 1,2-diol get cleaved, and we are going to get our target molecule here. Target molecule. This target molecule, which one? This is our target molecule. This one is a CS3, then OH and OH. This is our target molecule which we have seen. So in this way we have synthesized this molecule starting with the precursor or the chiral precursor. Chiral precursor means what? There are the chiral centers are 1, 2, 3, 4 chiral centers are there. This is a by using as a Chiron approach how we have synthesized this one. So understood this one, how do we can prepare, we have synthesized. This is the what we can call it as a synthesis part, half part. Now for what we can call for more information, let us see the mechanism of this step by step, how we can show the mechanism, probable mechanism over here. Third part, that is not for an exam point of view, but it is for your understanding, so that you can understood the how we can prepare this compound in the laboratory by keeping the suitable or the proper solvent. Now let us look at as a mechanical mechanism of this mechanism, how we can show the probable mechanism. And as we know that mechanism is a language of organic chemistry. If you know the language very well, you can express your thoughts very easily or effectively. Now mechanism, what is the starting compound of we have taken here? Here is, I think, this one, C double bond O. Mechanism point of view, we are writing this one. Then here 1 and 2, this hydroxy group are present over there. Then 3 hydroxy group I am writing here. This is the structure of D Mannose. This is the structure of D Mannose. Then this one further treated with, for mechanism point of view, boron, hydrogen atom, one hydrogen atom, another hydrogen minus, and Na plus is written over. This hydride get transferred from here to here, OH, and now what do you get over here? And here you are going to get this one. Suppose as a O minus here, I am writing shortly here, HO, then HO, then OH, then OH, and the OH, right? When negative charge on the oxygen atom, as we know that carbonyl carbon is a more electronegative in nature, so the hydride get transferred, attack on this carbon atom and O minus, and we are getting at this one, and then that we are using as a solvent, this reagent we are employing in a methanol. So methanol HO and Me we can write, this OH can be attacked over there, and you are going to get finally as this one OH and HO, this alkoxide can abstract the proton from solvent, and we will get as a this structure mannitol over there, right? This is the structure of mannitol, D Mannitol. D Mannitol. Why D Mannitol? Because this hydroxy group at second position, hydroxy group on the right hand side, and therefore it is a D Mannitol, right? Now next one, what is the next thing we have carried out? Then next one we are protection, right? Now acetone, as we know that C double bond O in presence of the H. Now what is going to happen? This lone pair which is attacking on this carbonyl carbon, and this is attacking at this carbon atom, and there is a removal of water molecule here in presence of suppose EH over there. Removal of water molecule takes place here. Similarly in this case also, C double bond O, this one, so OH is attacking over there, this is attacking over there and removing this one, water molecule, 2 moles of H2 is removed. What do you get? You are going to get over here, this one, here is O, this one, again OH, one OH over here, in this case also O, this is the structure, that is a protected D Mannitol we got here. And now this bond is going to break. How it is going to break over there? Let us see the proper thing in this case. Now the what we are using here, we are using as a lead acetate, right? Pb, then OAC. Now OAC, here OAC, and here also as a OAC, right? Now this hydroxy group is attack on this Pb, OAC get removed. Similarly, this is also attacking over there and it is removing. So the single bond get rotated and we will get finally, so what type of the structure you are going to get over here? So see here this type of the thing we are going to on. This part you can call it as R, another part also as R. Here O, then Pb, OAC, then OAC, Pb. So like this structure you are going to get over there. So now what is going to happen? This bond is a break. This bond is going to break to form as a double bond over there, and this bond is forming here, and these go along with that lead. So this is a probable structure because we know that mechanism is a hypothetic. So we are writing as a probable mechanistic steps over there, and you are going to get here 2 moles of this one CHO, and then this one O, and this, right? This is a structure we are going to get over there. So this is the mechanism of this mechanism, and now further this one treated with CHOOH, further used as a Rane nickel. As we know that Rane nickel, what it will do, it will convert this CHO group into as a alcohol. So OH, then O, this is a mechanism, a probable mechanism we can show over here. Here just remember as Rane nickel will convert the aldehyde group into as alcohol. And now next one, what is going to happen here? We are using as a tosyl in presence of the pyridine. And now pyridine, what it will do? It will pick up the proton from here, and the oxygen atom get negative charge, and now you are going to get here O minus this O, that type of the structure, right? And now this tosyl, TSCl, and as we know that TSCl, or we can show here the structure, full structure over here, this one, Paratoluene sulfonic chloride, it is known as CS3. Then S double bond O Cl. So this is going to attack over there, and then we are going to get finally here. In short, we are writing here again OTS and this remaining O and this one, right? This is a structure we are going to get over there. Now I am writing for the mechanism purpose. So let us clean the board first over here. And now what is going to happen in the next case, in the next one, OTS. So this one further treated with, what is the reagent we are using? That is the sodium iodide in presence of acetone, right? Acetone used as a solvent over there. That minus is going to attack on this. This is a good leaving group. Why it is a good leaving group, I will tell you later on here. So here is the iodine, then O and this get. Now when OTS minus, here let us look at here, OTS minus is an excellent leaving group, C double bond O, this one, because it is well stabilized due to the electron withdrawing group of S double bond O, and therefore we can draw the resonating structure here, C double bond O, SO minus, then double bond O, then here this group, right, as it is CS3, right? So this is a structure you can write over there. And now here we, after that, what you can use, again use as a Rane nickel. Rane nickel, there is a transfer of hydride, and what you are going to get, this becomes as a CS3, and you will get as a this one as it is. And then a mechanism of protection and deprotection that we already learned while studying as a there. So in case of the H2SO4, what is going to happen? This will pick up the proton from H, O, SO3, H, like this, get protected, and that cleave this bond, and you are going to get finally as a CH3 and then OH and the OH. This is our target molecule, and as we know that target molecule is nothing but what is that? The molecule whose synthesis is being planned is called as a target molecule. See this, so in this way we have completed as a first molecule. Tomorrow we will see the another molecule, that is a RNAS epichlorohydrin. I think with this wrap up today's lecture. We will remaining thing we will see the next time. Thank you. Have a nice day.